part of the learning target or the goal for today's class is that you're going to be able to explain why carbon, which we already looked at in the build an atom simulation, has 6 protons and 6 neutrons, which should be a mass of 12, but it's actually 12.0171. Okay, so we're not directly going to answer that question during this video. That's a question that you are going to be able to apply what you learned today to answer. Instead, we are going to look at a different atom. So we are going to look at an atom of chlorine, okay? So we know that chlorine has 17 protons and 18 neutrons in its normal, stable, ground state, however you want to describe it, in the regular atom that we've talked about, okay? So 17 plus 18 should be 35. But on your periodic table, chlorine doesn't have a mass of 35. It has a mass of 35.45. So the question is why, okay? What we know is that the mass that's listed on your periodic table is actually what we call an average atomic mass, okay? Some of you have already caught on. Oh, average. Duh, that's like math. When I add things up and I divide and I get an average, okay? So that's exactly what we're talking about. An average atomic mass means that there are various different isotopes, okay? Hopefully that term isotopes at least rings a bell from the build an atom simulation. We maybe didn't dig into it too much, but we at least kind of addressed it. So isotopes, remember, have slightly different masses, okay? So if we're taking chlorine as an example, one atom of chlorine might have 17 protons and 18 neutrons. Another atom of chlorine might have 17 protons and 17 neutrons. Those would be considered isotopes. They're still chlorine because they have 17 protons. Again, remembering back to build an atom, the number of protons is what determines what atom you're looking at. So as long as it has 17 protons, it's still chlorine. The difference is the number of neutrons make them slightly different, and they're called isotopes, okay? So what we have in the real world is we have different isotopes that exist, okay? So if I could pick up a handful of chlorine atoms, I might have some chlorine 35 with a mass of 35, 17 protons, 18 neutrons. I might have some chlorine that has a mass of 34 with 17 protons and 17 neutrons. I might have some chlorine that has a mass of 36, okay? What we find when we look at the periodic table is that there is an average atomic mass. No matter what sample of chlorine I pick up, on average, one atom will have a mass of about 35.45. Some will be a little bigger, some will be a little smaller. The average size is 35.45, okay? The way scientists calculate this is by something called natural abundance. So they have to figure out, in that sample of chlorine that I have, how much of it has 18 neutrons? How much of it has 17 neutrons? How much of it has 19 neutrons? Okay? So they find the abundance of each isotope, or how much of each isotope naturally exists. Okay? The process of doing it is actually pretty cool. Okay? So if we look at this example, because it's a little bit easier to picture before we get into this machine that actually calculates it. So if we think about this example, you're standing on top of a really, really tall building, or maybe you've seen some of those videos where those guys throw random things off of the really high wall, okay? What happens is the wind picks those things up. As they're falling down to ground, the wind picks them up, and the heavier something is, the less the wind can affect it. The lighter it is, the more the wind can affect it. So if you look at this example, you've got a tall building and you're throwing a bowling ball and a basketball off of the top of that building. Okay? So if you throw the basketball off the top of the building, it's filled with air, right? It has less mass, still has some mass, but less mass. The wind is going to be able to pick that up and take that farther. It will not fall as directly in a straight line. If I take a bowling ball and I throw that off the top of the building, okay, more mass, it's solid, it's dense, The wind doesn't pick it up as much, so it drops straight down the side of the building, or relatively straight. Okay, imagine a ping pong ball. Very, very, very light mass, very little. Okay, I take that ball, I drop it off the top of the building. Wind picks it up right away, carries it, it lands way far away from where I dropped it. Okay, so that idea, have that picture in your mind. That's exactly what scientists do to find this percent abundance or this natural abundance. They take a whole bunch of atoms. Let's say we're talking about chlorine. They take a whole bunch of chlorine atoms and they run them through a machine. And the heavier something is, the less it is affected by the machine. The lighter something is, the more it's affected by a machine. And based on where those atoms end up, whether they traveled on a straight path or their path curved because they were lighter, they're able to tell how much of each type of atom there is, okay? So all of that to say, this process gives us a percentage. So of my sample of chlorine, 85% of it has 18 protons. 15% of it has 17 protons. I can then figure out what the average, 17 neutrons. I can then figure out what the average mass is of that whole sample, okay? So tomorrow, we are going to specifically look at how to calculate that, okay? We'll get into the math. It'll become a lot more concrete. Today, the important part is just to be able to understand that the mass that's on your periodic table is an average atomic mass. I am not going to find one chlorine atom that has a mass of 35.45 AMU. That 35.45 is the average of multiple different atoms based on how many of them really exist in nature, okay? So if you go on to the next screen, you're going to see an understanding check where I'm going to ask you about that carbon atom that we talked about at the beginning. I'm going to ask you to explain, why does carbon have a mass of 12.0171? Okay, you should apply what we just talked about, the understanding that we just developed with chlorine, to explain what's going on with that carbon atom, why that number is the way it is on the periodic table. You'll get some feedback. Hopefully you're catching on and you're ready for the calculations tomorrow. If not, this is a great time to come to office hours or to check in with whichever science teacher is part of your house in the blended model, get a little bit further information from them.